All right, and we're back. So this is going to be the rest of the 7.3 notes here, guys, looking at enthalpy. So we last left off with making a diagram looking just like this, okay, in this example. Now we're going to get to what we're trying to really accomplish, which is, well, if I put in an amount that's not proportional to what's found in the chemical reaction, how much energy really does change. So it's to say this, okay, or actually, well, let's just go through it first. So delta H, the change in enthalpy for a reaction, sometimes known as basically the change of enthalpy of a reaction, that's just subscript reaction, that's all it means, is the enthalpy change for one occurrence of that reaction. So in this case, it would look like this. So here we have this example with butane, butane here, we have 1 mole of butane reacting with 5 moles of O2, and it's going to produce to us what we expect to be produced is 3 moles of carbon monoxide and then 4 moles of H2O. And that should give us a change of enthalpy, a change in energy here of negative 2,043 kilojoules. It's losing energy, okay? It's an exothermic reaction. So what we can do here is we can use the ratio between the number of moles of any one of these guys and also the amount of energy we expect to be gained or to be lost in a particular equation. So it's to say this. Okay, so what would the enthalpy change be if 12 moles of O2 were to react according to the above equation? So it's to say that, okay, instead of having 5 moles of O2, we have 12 moles of O2. How much more or how much less energy is going to be made here? Or not made, but sorry, lost or gained. So, and it's assuming that this is going to be proportional, that the amount, or that there's going to be an excess, or there'll be a proportional amount of butane that'll react with the 12 moles of oxygen. So, okay, so it's just this. We're doing what we have been doing like in Stoic, okay? So we're going to write down the given numbers, 12 moles of O2, because that's what we're inputting into the system. And we're going to convert these moles of O2 we're putting into the system to the amount of energy we expect to come out. And the way we can do that is using, again, we're going to use a ratio between the normal number of moles used up in the equation and using those normal number of moles, how much energy we expect to come out. So moles of O2 is, this is our old product, and we're going to want to get rid of that. And we're trying to see how many kilojoules worth of energy is going to be, in this case, lost. A whole lot of stuff to say that we're going to put the number of moles found in their chemical equation of our particular substance, which is O2. And then up top, we're going to put the amount of energy we expect to be produced. I keep saying that. Not produced, but lost in this case. Okay, so it's going to be this times this divided by this. And keeping sig figs, which is just going to be 2, our answer should be 4,900 kilojoules worth of energy. So we expect that we're going to have 4,900 kilojoules worth of energy lost here. Okay. So again, it's like the same thing that we've done for Stoic. The only difference is we're like adding a different step. And the step here is saying that under normal circumstances, on our balanced equation, this is how many moles of O2 that are normally used. And when that is normally used, when combusting with this stuff and producing this stuff, this is how much energy we lose. And so here we're just saying that, okay, here's our ratio. If we put this all together, this is what we expect to be lost, okay, in this equation. Now, this one was easier because it gave us our number of moles, because you can just go straight from moles to kilojoules. But in this problem here with methane, they give it to us and they give us the mass of methane rather than the moles of methane, so we just have to convert mass to moles and then moles to kilojoules. So in this one, it's asking how much heat is transferred when 19.22 grams of methane burns in an excess amount of O2 according to the following equation. This excess, all that means is that there's plenty of O2, that what's the limiting reactant is this stuff. You'll run out of this before you run out of O2. So we're just focused for the reaction and measuring how much energy is lost or gained. We're only caring about this stuff because there's plenty of this stuff. Okay, so it's 19.22 grams of this. Okay, and here again, we just got to go from grams to moles. And so we're going to use the molar mass of methane. So in every 1 mole of methane, okay, there are 114 grams of methane. That's just 18 plus 14 times 8. Double check that. 12 times 8. Sorry, 12 times 8 plus 18 gives us 114. Okay. Ooh, does that seem... Hold up. Let me double check that real quick. That seems right, but I just want to double check. Yep, that's right. Okay. Oh, and that equals... So you know, grams of methane cancel out, we're left with moles of methane, and now we're going to multiply one more time. So if we were to solve up to here, we would then have moles of methane. So now we can go from moles of methane to kilojoules of the overall reaction. And so in this case, it looks like we have 2 moles of methane in our reaction, and when we have a proportional amount, we expect 2,803 kilojoules to be lost, a negative 2,803. So moles cancel out, methane cancels out, and then we put all this together, and keeping sig figs, we'll have a negative 236.3 kilojoules worth of energy lost in the system. Okay. So if we were to, what's the saying is that it's saying that if we input this amount of mass of our methane into the system with an abundance of this stuff, just how much energy is going to be lost or gained, and this is how much we are going to lose. Okay. And so now that's what we practice in the beginning, and here's now just adding a bit more to it. So this again is, these two problems are assuming that so for this one we're assuming that, yeah, the 12 moles of O2, but we're assuming there's an excess of butane, so we don't have to worry about this running out. We're worried about this running out. Okay, so if this runs out, you know, you won't have a chemical reaction, and so when it runs out, how much energy is going to be lost or gained, and so then we calculated that. For this stuff down here, for methane, it's the same deal. We've got a limited amount of this stuff, excess of this stuff. We won't run out of it. So when we run out of this stuff, how much energy do we expect to be, in this case, to be lost? This is how much energy. So in this problem, it's now saying, okay, you have a limited amount of nitrous oxide here. You have a limited amount of nitrous oxide, and you have a limited number or limited amount of water. Create an enthalpy diagram in this reaction. Let's just focus on what we have to do first. So here, what we have to do is we have to determine who's going to run out first. In other words, we have to figure out who the limiting reactant is. Okay, because again, in this case, one of these is going to run out, and we don't know which one's going to run out. So we're going to set this up like we did with BCA charts. So we're inputting 147 grams of NO2, and we're inputting 100 grams of H2O. We're going to figure out who is going to run out first. And so I'm going to walk through this as if it is just like it is whatchamacallits. Like we're doing this, like figuring out the limiting reactant on a BCA chart. So in every 1 mole, so I got to convert mole or grams to moles here. So in every 1 mole of nitrous oxide, we have 46 grams nitrous oxide. Every 1 mole of H2O, we have 18 grams of H2O. Okay, now here's where we're going to change things. So remember in BCA charts, this number that we're about to put down, I said like keep it to a bunch of different decimal places. We're going to actually keep sig figs all the way through. So we're going to keep sig figs, so we get 320 or 3.2 out of this. And then down here, we're going to get 5.56. Okay, so these are the number of moles for our substances. NO2, H2O. But now we've got to divide by their coefficients. So for NO2, it's 3. For hydrogen, it's just 1. Or from water. And we're going to see which one is going to run out. So this guy's 5.56. While this guy is going to run out, it looks like, because it's 1.07. Okay, much smaller than this guy. So here is our limiting reactant. So we're first going to run out of NO2. And because we run out of NO2, we really only care about this stuff. Okay, we don't care about the water. There's an abundance of water. We'll have excess water left over. So now what do we do? Well, look at it this way. What we've done up until this point is actually what you have done on the back. Like we've done this step right here, we've done this step right here, and then you did like half this step right here. You took whatever the number of moles is divided by the coefficient, but we've left out the amount of enthalpy we expect to see under normal circumstances. So what have we taken out? We've only taken out multiplying by our change in enthalpy. So we're just going to multiply this 107 times negative 138 kilojoules in this case. And we're going to figure out just how much is actually going to be lost. And if when we put this in, we're going to actually lose negative 148 kilojoules. Okay, so again, we have now lost negative 148 kilojoules worth of energy now that this is all said and done. Okay, now this is put up a little differently, of course, than what we just did a little bit ago, but it's really just, again, to make things a little bit, I guess, to just, because you guys have that muscle memory, you've got that just typical memory of doing work for BCA charts like this. Okay, this is fine. If you actually want to do, or you see whichever one has the lower amount of energy, that's pretty much the same thing. And using the work that looks like this. Okay, if you were to do this for both of them, that works too. Again, this is just to kind of show you that that we're looking for the limiting reactant, because whichever one runs out first, that's the one we need to focus on, because once that runs out, you don't have a reaction. Okay, so, all right. And now the last thing we have to do is draw an enthalpy diagram. And so here's what I was mentioning in the other video about how when we're making these, we have to make sure that we are writing in the correct amount of enthalpy, the right amount of change here. So in this case, with the amount that we inputted, okay, with the amount that we inputted, we have to show that this is how much change we had. So this is an exothermic reaction. So this is exothermic, okay, and we're going to lose energy in this system. And so in this case, though, how much did we lose? Well, if we inputted the 147 grams of nitrous oxide with an abundance of H2O, here is how much we're going to lose, negative 148 kilojoules. So when questions ask you, because you're going to have questions that are going to ask you to draw these diagrams, you got to make sure the diagrams include the proper amount of energy change. So if you were to put this down, the negative 138 kilojoules, that's going to be wrong. You'd get that marked off, either be minus 1. Okay, got to make sure that you include the correct number of kilojoules that will change in the particular problem that we're working with. Okay, so all right, and that is it for these notes, guys. So if you still have any questions for me, make sure you ask. If not, I'll see you in the next one.